Do we have quiz or something? No? Okay, good. Why you come so on time? Okay, good. The class starts at 12:40. You already here. Good. Okay. It should be normal, right? For me, it is not normal. Okay. Now, let's start. And we should have a quiz maybe sometime. Okay, next week or the week after. Okay. Once a while, you should read the book. Okay, and make sure you understand them. Last week we talked about memory management. Okay, using like partition, using the paging. Okay, and again the paging is the idea that we can divide our process into many pieces, into many pages. Okay, and put the page into the frames. Okay, which is the partitioning of the RAM of the memory. Okay. And then later on, if we still have using the fixed size in terms of paging for each frame, we still have the internal fragmentation. Okay, so to get rid of internal fragmentation, okay, of the last frame, okay, of each process. Okay, so we can do the segmentation. Segmentation is similar idea with paging, but it's that the size of each frame doesn't have to be the same. Okay, so we can fit the page that is too small. That's smaller than the size of the given frame. Okay, so then for that case, to calculate the physical address, you need to find the beginning of that frame and then find out how far from the top to the bottom, and then add them up, then you would know the actual physical location. Okay. Another part of this memory management is a part that OS should concern. Okay, it's in terms of security. Okay, because today with the modern technology, every machine likely to connect to the network, and network connect to the internet. Okay, so it's likely that our server may be attacked, by the bad guy, or maybe your local personal computer or mobile. Okay, so then for that case, security issue on the memory, should be addressed. Okay, like for example, if this part of the memory belong to process A, should process B use this part of memory? No. Okay, so for this case, OS must mark in the page table like this, to tell where are the pages of this process in the page table or segment table. Okay, so then if other process try to access this address that belong to another process, OS would not allow. Okay. And another one that is also interesting is that sometimes OS allow one process to grow, because actually sometimes we don't know in advance how much memory that we're going to use for each program. Okay, so when you run the program, process make use more and more memory. Okay, so at certain point we may running out of memory. Okay, so that's why OS likely to have limit amount of memory to use by each process. Okay, because sometimes you have the bad guy try to occupy too many memory. Okay, so it's called the overflow attack. Okay, that one process likely to grow a lot quickly and look like it's not a normal program that keep growing the memory for that program, for that process. Okay, so OS must try to detect whether one process keep calling more and more memory quickly or not. If that's the case, that should be the attack. Okay, so then OS may have to kill that process. Okay. Okay, I will stop at this one for the memory management. Okay, now the next topic is the extension of the memory management is the virtual memory. Okay, again, the concept of virtual memory is that, okay, at certain point, okay, we might not have enough memory in the computer, okay, but we want to run a lot of process, and also we want to allow a big process to run. Okay, so if we have limit amount of memory in the RAM, a big process or many processes cannot run in the system. So that's why OS try to reserve, okay, the secondary memory, which is the hard disk, okay, to reserve some part of hard disk, okay, to make the system to look like we have a big memory. Okay, in other words, make a RAM look bigger, but actually it's not bigger. The RAM that you buy, okay, with this size is still this size. Okay, you cannot change the size of the RAM after you bought it. Okay, however, OS try to say that, oh, we have another part of RAM, another part of memory. Okay, but that use the hard disk. Okay, and that's the virtual memory. Make the space in the secondary memory look like a part of the space of the main memory. Okay, that's why they call virtual. Okay. You know this person? Have you born at that time? You know this movie? Okay. You know this movie? You mean you are old? I only born at that time. But I'm too young. And I watched this movie when I was young. Okay, we're gonna need a bigger board. Okay. And here, not the board, we're gonna need a bigger memory. Okay, when you want to run a big system. Okay. Again, so we need to have the hard disk, okay, to help us, to make it look like we have more memory. Okay. Actually, the first part of this chapter, they show you in terms of hardware structure, which is something I'm gonna skip, okay, because we're not dealing with the hardware, we're dealing with the OS. Okay. So the one that OS is, I think, on the second part. Okay, this is the hardware part. Concept is similar. Okay, you have to be able to, okay, manage the hardware, the hard disk, okay, to make it look like it's a part of the memory. Okay, you have to do the address translation. Okay, sometimes if you extend to the virtual memory, now your hard disk, okay, some part of hard disk will make it look like it belongs to the RAM. So in other words, the memory will look like it's much bigger. When the memory is much bigger, the address will need more than what you have in the RAM. Okay, so the address translation may need to be a little bit more complex because the address is like two parts. One is in the main memory, another part is in the secondary memory. Okay, so you have two lists of address that you have to deal with. Okay, so sometimes you have to do like two-level paging system. Okay. I'm gonna jump to the part that belong to the OS. Here, OS. Okay. In terms of software, the OS have to manage this part of memory. Okay. In other words, the secondary memory, the hard disk, to make it look like main memory. Okay, so that some part of the program, okay, will remain in the main memory, some part remain on the secondary memory. Okay, but like I mentioned before, okay, OS, okay, will send the instruction on the memory, okay, to run with the CPU. Okay, CPU will know only the address on the main memory. CPU doesn't know address on the hard disk, on the virtual memory. Okay, so for that case, if the part of the program that remain in the virtual mem need to be executed, okay, OS have to copy this part from the secondary memory into the RAM first. Okay, after they copy into the main memory, then the CPU can grab that instruction to run. Okay, so the problem that OS have to deal with is that some part of the program remain in the main memory. Okay, another part of the same program remain in the virtual mem. So OS have to copy the part that need to be executed at this time into the RAM. And also mean, okay, let's say, for example, let's say it is your RAM. Okay, let's say you keep one process, let's say 8 megabytes. Okay, If this process need, let's say, 10 megabytes, what does it mean? 8 megabytes will remain in the RAM. 2 more megabytes remain in the virtual mem. Okay, but let's say OS give at most 8 megabytes for each process to stay in the RAM. Okay, 8 megabytes remain here, 2 megabytes remain outside. Okay, most of the time the OS will send this instruction on this 8 megabyte to run. But if some instruction in here need to be used, need to be executed, so then OS have to swap this one in. However, if OS swap this one in, what happened in this one? You still have only 8. So if this 2 megabyte gonna come in, so 2 megabyte in here have to be swapped out. So you have to swap 2 megabyte between the two. Okay, and that's the issue of OS. Okay, have to make sure that this the one that need to be executed going to swap into the main memory, and some part of this process which is in the main memory supposed to swap out to make room for those one outside to go in. Understand? Okay, so that is issue. Okay, that OS have to concern. Okay, again in terms of virtual memory, OS should be able to support paging and segmentation to be able to use between virtual memory and main memory. Okay, the one that I mentioned is called the replacement policy. Okay, there are many of them. Okay, the one that I said you have to swap some of them in, swap one of them out. Okay, one of them is called replacement policy. Okay, what is replacement policy? If you have this 8 megabyte, okay, if that 2 megabyte on the virtual memory, or in other words on hard disk, need to swap in, the question is, among these 8 megabyte, who should be swapped out? I mean, you have 8 megabyte, 2 megabyte should replace on top here, or over here, or over here, over here. Agree? You have like 4 choices among 8 megabytes. If 2 megabyte you have to load in, it could be 2 on the top, second 2 megabyte, third 2 megabyte, or last 2 megabyte. So one of these 4 gonna be swapped out. The question is, which one? Last one? Why last one? Oh, it depends. There are policies that you should use. Okay, that which part should be swapped out. Okay, we know for sure this one gonna swap in. Okay, they're gonna replace one of these 4, but which one should we replace? The one the system does not use. Okay. Which one that does not use? That's good. It's true. The one that you're not gonna use, why you have to remain in main memory? If the one that you're gonna use, let's say you swap this one in. If you know, let's say the third piece, you're gonna use it soon. So we should not replace the third piece. Because if you swap the third part out, later on you're gonna use the third part, then you have to swap the third part in again. Agree? So you should swap out the one that you're not gonna use. But which one we not gonna use? So depend on the policy. Okay. The best policy they call optimal. Okay, optimal is say that if we know the future, we know that after we load this 2 megabyte in, and let's say after we finish execute these 2, which one we can execute next? The one we're going to execute after that, we should not replace it. Agree? Let's say you have 4 choice, 1, 2, 3, 4. Okay, if we swap 1 and 3, the outside with the 3, okay, and 3 going to use soon, we should not choose 3. Agree? So if soon after this we're going to use the third 2 megabyte, we should not replace the third 2 megabyte. Okay, let's say among 1, 2, 3, 4, let's say the one that we're not going to use in near future is 1. Okay, let's say after this we're going to use 2, later on we're going to use 3, after that we're going to use 4. Look like 1 not going to use in the near future. Then we should swap with the 1. Because 1 not going to use soon. But if you know that 2 going to use in near future and you swap with 2, then in the near future you're going to swap 2 back in again. So it's just wasting time, swap in and out, in and out. Okay, so the optimal is say that you look to the future. Okay, in the future, the one that not going to use in the near future, in other words, one going to use furthest away or not use at all, that one should be swapped out, should be replaced. Okay, but the question is, does OS know the future? OS just pick one instruction at a time and execute, pick one and execute. They don't know what in the future, which instruction. Actually, OS never know the future. OS just pick the current instruction. They don't know that this instruction going to say if and then jump to those instruction. They don't analyze the whole program. Okay, and the program sometimes depend on user choice. User choose this, they do this part. User choose that, do another part. So OS cannot really know the future. So optimal is ideal. Okay, but it's not real. Okay, so they have something else like least recently used, first in, first out, that we're gonna learn. Okay, what are other practical replacement policy? Okay, they also have fetch policy. Okay, placement. Okay, where to divide the memory. We look at it after this. Okay, and the cleaning policy. Okay, what is fetch policy? Okay. Fetch here, we're talking about not the fetch between CPU and memory. We're not talking about that fetch. Okay, we talk about between memory and the hard disk. Between memory and hard disk, which is the virtual memory. Okay, so question for fetch policy is that, okay, when should we load the page from virtual mem into the main memory? Okay, for example, you execute instruction 1, 2, 3, 4, 5. Okay, let's say you execute instruction number 10 now. Likely that later you're going to execute instruction 11, 12, 13, 14. Okay, let's say you have 20 instructions here. Okay, and then 21, 22 outside. Okay, let's say you execute up until 10. You know that soon you're going to execute 11, 12, 13, and also 20, and then 21, 22. Okay, the question is, if you execute all the way until 20, okay, and at that time you're going to need instruction number 11, but it is not in here. So what we have to do? We have to swap that 21 in here. Okay, the time that to copy from hard disk to the RAM is a long time. Okay, because hard disk is like external from the motherboard. Take a long time to copy. So if you execute until 20 and then wait for the copying from virtual main memory to the main memory, virtual memory to main memory, that would take time. Okay, you will waste the CPU time of not doing anything. Okay, so if you execute until 20 and you will wait the one that you need to copy in, that one is called demand paging. When you need it, you're gonna demand it and send that one in. Okay, but if it would be better if we execute up until 10 and we know that, oh, I'm not going to use 1 to 9 now. Okay, and later on I'm going to use 11, and in the near future I'm going to need 21, which is not in here. Okay, so pre-paging say that if we know that somehow, somewhere after it we're going to need that one, why don't we load it first before the time that we need it? That's why they call pre-paging. You load it in ahead of time. You don't wait until you really need it and then load. Understand? The demand paging say that, okay, you're not gonna load the instruction or data from the virtual mem, okay, ahead of time. Demand paging said by the time you need it, then you load in. Okay, but that is wasting time of waiting, because you have to wait, okay, the system to load from hard disk to the main memory. Okay, so again, if you don't want to wait, okay, why don't we load ahead of time? Okay, before we get to that point, we load in first. Okay, during the time that you load, you execute instruction 11, 12, 13, 14. Maybe by the time you finish execute instruction 15, you already have 21, 22 there. Okay, so by the time you get to 20, you don't have to wait. 21, 22 is there. That's called pre-paging. Okay. So why do we need demand paging then, if we have pre-paging? Oh. program always have some kind of if this, we do this. If not, we jump, we do over there. Okay, so sometimes you do pre-paging, but by the time you get there, let's say you have if on instruction number 19, and then instruction 19 said, if it is not true, jump to 25. You might not need 21, 22. That's the disadvantage of pre-paging. Sometimes you load in, but then you find out later you're not going to use it. Okay, so that's why the good point of demand paging is that we don't know the future, what would happen. We don't load it ahead of time. Okay, it is called fetch policy. What do you think? If you are the OS designer, which one you prefer? Demand paging or pre-paging? Depends. So what do you think? Which one it should be? Most OS would use. They use both. Okay. Okay, but likely that pre-paging will be used. Okay, because the disadvantage of demand paging, like I said, okay, is that you have to wait, and sometimes waiting it takes a long time. Okay, pre-paging, if you load it, you don't need it. It just wastes your memory that you load something in but you don't use it. But in terms of system-wise, you try to take advantage of the CPU utilization. You don't want CPU to wait. Okay. Okay. That's the one that I mentioned. Now, the second issue, that is not really big issue, okay, of the virtual memory is placement policy. Okay, where should we place the process? Okay, again, the difference between placement and replacement is that, okay, where should you load this process or that instruction from virtual mem into the main memory? Okay, if your memory is not full, it's no issue. You can place anywhere you want. Okay, that is a placement. Okay, placement is not a big issue because you can choose any place you want, any frame that you like. Okay, but the one that big issue is replacement policy. Now, when the time that you already have full memory of that process, okay, you have no more space left for that process, then you need to swap in and out. Okay, that's a replacement. Okay, but placement is not really big issue. You can place anywhere you want. Okay, but as long as you don't place in another part that belong to another process, you can place only the frame that belong to your process. Okay, but the big issue, like I said, is replacement. Okay, we have to replace one page with a page from the outside, and at that time you copy that page to the outside. Okay. Okay, we look at the policy of replacement policy after this. Okay, frame lock. It also is a part that OS may have to concern that this frame, it already locked, belong to this system or not. If it belongs to the system, belong to the kernel, the OS should not assign this frame to any other process. Okay. In terms of replacement policy, okay, there are many of them. This is just 4 examples of the replacement policy. To choose the memory, okay, choose the page number, okay, that we're going to replace, okay, by the page from the outside, the page from the virtual mem. Okay. Okay, again, the key, okay, we want to make sure that the page from the outside that going to replace the page inside the main memory, okay, should not be the page that we're going to use in the near future. If we replace on top of the page that we're going to need in the near future, okay, we're going to need to load in again, in and out many times. Okay. Okay. Let me look at something simple first. First in, first out. Right? First in, first out. What is first in, first out? The one come first. We're going to replace that one first. Okay, let's see for example. Okay, let's say this is your memory for this process. That's an example. Okay, let's say this process, okay, had been given 3 frames. Okay, actually there are a lot more memory up here, down here, okay, but they don't show here. Okay, let's say only 3 frames, okay, are given by OS to this process. Okay, there are 3 frames, 1, 2, 3. Okay, and then let's see for this process, okay, they need 5 pages. You look at the number between 1 to 5. Okay, let's see a process, this one need 5 pages. Okay, but OS give them only 3 frames. So it means that 3 frames can remain in the memory and 2 frames remain outside on the virtual memory. Okay, so if you already occupy these 3 frames and then you need 1 more outside, then you have to swap. Okay, for this example, they don't care the one that you swap out. Okay, they care what to swap in. Okay, for example, let's say this is the way that this program execute. This is a page number that this program gonna need. Okay, so let's see the first time this process gonna need the page number 2, okay, to execute. Okay, so OS will load page number 2 in, okay, these 3 frames, one of these 3 frames. Okay, and then later on they need page 3, load page 3 in. Need page 2, there is no need to load in because 2 already in there. Okay, and then later on need page 1, so load page 1 in. Okay, and let's see after that they need page 5, which is not in here. Okay, and this process running out of memory frame because OS give this process only 3 frames. So if we running out, so then one of these gonna be replaced by the new one, page number 5. The question is, who should we replace, 2, 3, or 1? Okay, so if we use first in, first out, the one come in first, that one out first. For this case, among 2, 3, 1, 2 came in first. Okay, so 5 will replace 2. Okay, so you will have 5 on top of 2. In other words, actually you already copied 2 out, okay, before you replace 2 with the 5. Okay, and then later on we need 2. Now if we need 2, but 2 is not in here, so 2 going to replace 3 because 3 came after 2. Among 5, 3, 1. Okay, among 5, 3, 1, 5 come in at this time, 1 come in at this time, 3 come in first. Okay, among 5, 3, 1. Okay, 3 come in first and then 1 and then 5. So if the new page need a frame, so they're gonna replace 3. Understand? 3 come in first among 5, 3, 1. Okay, and then now a process need to execute page 4 and page 4 is not in here. Okay, so 4 gonna replace among 5 to 1. So among 5 to 1, who came in first? 1 came in here. Okay, 5 came in here, 2 came in over there. Okay, so 1 came in first. Okay, compare between 5 to 1. So 1 came in before 5, before 2. So 4 gonna replace 1. Understand? Okay. And then after that, the process gonna need page 5. However, page 5 is in here already, so no need to replace anything. Okay. So another word, there is no F word. F means page fault. Page fault means the process need to execute instruction from that page, but it's not in the system. Okay. If it's not in the system, process need to load that page from the virtual memory into the main memory. Okay, so another word, for example, at this time you need page 4, but page 4 is not in here. This is page fault. If it's page fault, okay, we're supposed to replace 4 with one of these. Okay, but for this example, we need 5, and 5 already there. If 5 already there, this is no page fault, because 5 already there, no F. Understand? Okay, page fault means the process need that page. But that page is not in the main memory. We need to load that page from the virtual memory into the main memory. Okay. Okay, and so on. Again, page 3 need to be used, but it's not in here. So 3 have to replace either 5, 2, or 4. Okay, and among 5 to 4, look like 5 came in long time ago, before 2, before 4. So 3 gonna replace 5. Understand? Okay, And it is called first in, first out. Who comes first, that one going to be replaced first. Okay? Okay. So if we do this first in, first out, okay? Okay. What we want in terms of system, the system want to have a lot of page fault or want only a few page fault? Page fault is a good thing or bad thing? You want that page, but that page is not in there. That's a page fault. It's a good thing or bad thing? It's a bad thing. They want to execute, it's not in there. We have to wait and then to load it in. Okay, so the system doesn't want to have a lot of page fault. They try to minimize. Okay, think about if you want that page is there, good. You want again, it's in there. Okay, if you don't need to find out from the outside. Okay, the system want to reduce page fault. Okay, so with first in, first out, for this example, okay, we're going to have page fault 6 times. Okay. Okay, now look at another algorithm. Go back. Optimal. Okay, what is optimal? Optimal says, okay, if we want to replace a page, okay, from the outside on top of one page in the main memory, we should choose the page that we're not going to use in the near future. The one that we're not going to use in the near future, okay, if we choose the one that we use in the near future, what happened? By that time, we need that page. That page is not there. Agree? The one that we're going to use in the near future should not be replaced. The one that's not going to use far, far from now, that one should be replaced. So then we can cut down the page fault. Okay. Okay. Let's see this example. Okay, the same page usage. Okay, the same pattern. Okay, the system needs page 2, load 2 in. Need page 3, load page 3 in. Need page 2, 2 is in there already. Page 1, load 1 in. Now they need 5. The question is, they want page 5 and page 5 is not in here. We have page fault. The question is, 5 should replace 2, 3 or 1. With this algorithm, we look in the future. Look through the future. Which one not going to use in the near future? Among 2, 3, 1. Look at the future. Which one that we're not going to use in the near future? Okay, among 2, 3, 1, you can see here, at this point, we're not going to use 1 at all after this. So if we're going to replace, okay, we should replace the one that we're not going to use in the near future or not use at all. Look like, for this example, 1 not going to be used at all. So if we not really need page 1 anymore, we should replace with on top of 1. Okay, but if we replace 2, here we're going to use 2 soon. If we replace 5 on top of 2, now we're going to need 2 again. We have page 4 again. And that is the problem of optimal. Optimal is ideal, it's not real. But I try to show you that if it's possible, look at the result. What is the optimal? Optimal going to have the minimum number of page fault for sure, because you know the future. Then you choose only the one that you not really need or you not need soon in the near future. And like I said before, we don't know the future. Sometimes you may know the future. In some system, if your system is closed, you don't have arbitrary program. You know exactly what program going to run. You may know exactly what page going to need. Okay, in some closed system you can, but in most of the generic system, like most of OS, they are generic. When they are generic, you don't know what's going to be in the future. But if your closed system, you run your own program, you know exactly. Like for example, when you do project on Node MCU, okay, Raspberry Pi, you have only your own program. You're not going to run any other program. Then you know exactly which one you're going to need. Okay. So again, this case, okay, it's good for only the system that you manage every program by yourself. You would know the future. Okay. Understand from this point? Okay, again, now you can see you replace 5 on top of 1 and you're not going to need 1 in the future. So then you just put on top of 1. And now next one you need 2 and 2 are still here because you don't replace it. If you look at first in first out, 2 will be replaced, right? Use first in first out, 2 came first before 3 before 1, 2 gonna be replaced. If 2 gonna be replaced, now you're gonna need 2, you're gonna have paid fault. Okay, but for this case you're not gonna have paid fault when you need the 2. Okay, and again now we need the 4 is not in here. Who should we replace? Among 2, 3, 5 we need to load 4 in. So in the near future, which one not going to need in the near future? At this point, soon you're going to use 5, later you're going to use 3, after that you're going to use 2. So among 2, 3, 5, 2 is the furthest away, okay, that we're going to need. Okay, so for that case, 4 will replace the 2 because we're going to use 5 soon, and later on we're going to use 3. So look like 2 going to be far from now. Just replace the 2. Understand? Okay. Okay, again, this is optimal. Okay, if we know the future, we know which page that we're going to need in the future. But again, it's not real. But if you compare the page fault, how many times we have page fault? 3. Compare with first in, first out, how many times we have page fault? First in, first out. Here, 6 times. Okay, is double of the time that you have to wait if the page is not in there. Okay, so optimal, okay, likely to have minimum number of page fault. First in, first out is very simple. Agree? It's the simplest algorithm that you can develop. Okay, but you don't care how they're gonna be replaced, how they're gonna wait. They don't care. They just make a simple solution, simple algorithm. Okay, and that's why we have a big issue. A lot of page fault. Okay. Okay. Now if we don't know the future, we know only the past. Okay. Can the past tell us something? We don't know the future for sure. Agree? Okay. In our life, we know the past. We know the thing that we had done an hour ago. We don't know what the next hour is going to be. Can we use something about the past? Oh. Okay, there is an algorithm called least easily used. What is least easily used? When you run the program, most of the time program just execute next. But there are sometimes program have loop. Execute instruction 5, 6, 7. It is a loop. They go back to 5, 6, 7. Go back to 5, 6, 7, 5, 6, 7. Okay. Sometimes program have this kind of thing. If you have the loop, you execute 5, 6, 7, and let's say at that time you repeat 6. Zoop. If you have a loop, you come back. Now 6 gone. Agree? Okay. So many times in your program, you likely to have a loop. Sometimes you execute that one, you're gonna go back. Maybe use that one again. Okay. So if we cannot use the future, why don't we use the past to predict what likely to be in the future? Okay, and least easily used is the idea that, okay, likely that program, if you just call this part of the program, likely that you may call it again and again. Okay, most of the program do that. Like for example, think about your Microsoft Word. When you type your program, type document, which one that you love to use on the Microsoft Word? Some people panic, save all the time, save. You keep calling save many times. Okay, some people love to did spell wrong all the time, and then once a while spelling come up, once a while red thing come up. Okay, the thing that you likely to do, you do likely the same thing again and again. Or you do drawing on Microsoft Word. You shoot the lines, and then later on you shoot rectangle, you shoot oval, you keep drawing at that time. Okay, so most of the time when the human use application, they are likely, when they do something, they're likely to repeat doing things around there again and again before they jump to something else. And then when they go to that one, they can do something around there again and again. Okay, that's the nature of the people. Okay, so for that case, this algorithm suggests something we're going to replace the page that least easily used. What is least easily used? The one that we never use long time. The least. The one that we just use, most easily used, just used in a few seconds ago, that should not be replaced. Like I said, sometimes you go in the loop, the one that you just used, you got to go back again and again and again. Okay? Or you keep clicking save, and that person loves to click save and go back save again and again. That's the most easily used. The one that you just used. Okay, but they say that the one that we should replace is the one that we never used long time ago. Likely that when you use that one, you're not going to really use it again. Okay, that's this idea. Okay, to replace the page that we never used long time ago. It's called least easily, not most easily. Easily means now. Okay, the one that least easily is far away. Most easily is near, just a passive. Okay. Okay, so here least easily used. We don't look the future, we look the past. Okay. Here we need 2, load 2 in, need page 3, need page 2, need page 1. Now, if we need page 5, the one that we never used for long time, which one? Is 3, because most easily used is 1, sorry, and then 2, and then 3 long time ago. Okay, so 5 gonna replace 3. Understand? Okay, and again, by the time we need 2, okay, and 2 already here, it is not a page fault. Okay, and now we need 4. 4 is not here. Here the page fault. The question 4 gonna replace who? 2, 5, 1. The one that least easily used is from this point is 1. Okay, because we just used 2, and before that we used 5, and before that we used 1. So 1 gonna be replaced by 4. Understand? Okay, that is one that we never used long time ago. That one likely, okay, not to be used soon. Okay, the one that we just used, likely we're gonna use it again. So we should not replace the one that we just used. Okay. Again, for this case, 3 will replace who? 2, 5, 4. So look in the past. 5 we just used. 4 we used before 5. 2 is the furthest away in the past. Okay, so 2 is least used compared at this point. Okay, at this point, okay, we need 3, but 3 is not in there. Okay, 3 gonna replace either 2, 5, or 4, and the one between among 2, 5, 4, 2 is one that we used long time ago. So 3 gonna replace 2. Understand? Okay, again, due to the suggestion that likely the program gonna go back to the part of the program around there many times. Okay, if the program executes somewhere around there many times, the one that you just run, just use, don't replace it. The one that never run for long time, likely not to be used soon. Okay. Question? Understand? Okay. Again, just for this example, okay, it turned out that the page fault for this one is 4. Again, it depends on the way you use your data. Okay, the way that you execute your program. The program doesn't have to be pattern of execution like this. Okay, but for this example, you're gonna have page fault 4 times. Okay, but for this example, the one that works is first in, first out. First in, first out have 6 page faults. Okay, just an example. Okay, the optimal likely to have the smallest number of page faults. Okay, understand? Okay. That's the 3 example of the replacement policy. Okay, think about if I ask you to write program. I mean, optimal, you cannot write for sure. Agree? You don't know the future. Okay, you can write first in, first out. Easy one. Which one comes? You have a simple queue. Who comes first? Put them in the queue. Okay. How about if you have to implement least easily used? How to implement literally use?
You have to go backwards and like add the values to like an array.
In the array and
And anytime you get a duplicate value, you ignore it. When you have two values in the array, whatever the last one is has to be the least recently used.
if you have the duplicate,
You ignore it.
you
But if you have, in this case, two values in your array, since we only have three frames, once you have two values, then you know the third value has to be the least recently used.
oh, but again, okay. You can look, okay, at the way that you have these three value back.
Yeah.
Okay.
So you'd look at from 5, you'd look at 1, you'd store that, and you'd look at 2, and you'd store that. And since you've stored 1 and 2, then you know 3 has to be the one that goes.
Now, okay, the key issue is this kind of array, right? The way that you use, you have to keep swapping the place among these values that you just recently used. Okay, like for example, for this case, okay, you're going to need the 2, but 2 in there. Okay, so then you used to have like 5, 1, 2. 2 is in front of the queue. Okay, but now you just use 2. You have to take 2 out of your data structure and put 2 at the back of your data structure. Okay, so it's not really stacked because 2 could be anywhere in your data structure. Okay, but you have to find out which one and then you replace. Okay, and then you put something else in front of the queue. Okay. And also depend on the number of frames that you are allowed. If you have a large amount of frames, okay, this number gonna have a long list. Okay, and in terms of long list, it's gonna be harder to find out. Okay, is in there or not. Okay, so because you have to search in your list of the page number whether which one is in the list or not. Okay, if it's not the list, then it's faithful. Okay, if it's in the list, you have to move that one, okay, to the back and put something else in front. Okay, so the time of doing literally use algorithm likely to be a long time. Okay, it's possible, it's doable, okay, but it's more complex than first come first first in first out. Okay, because first in first out is simple, you just use a queue. Okay. So because this one is a bit more complex, okay, in the most of OS, okay, they try to adapt this one to be something simple version than literally used. Okay, it look hard for you, but it perform faster, okay, by the OS. Like this one, they call clock policy. Okay, clock policy is a policy again using in the Unix family. Okay, later on you have Linux. Okay, they have another algorithm look a little bit more complex by human, but is in terms of the algorithm of the program, it perform likely to run faster than the literally used. Okay, what is the clock policy? It is a clock. Okay, it look a little bit more complex. Okay, for you, but when you write code, it should perform faster than the literally used. Okay, the clock policy say that you have the clock. Do I have another picture here? Look like this. Okay, the idea of clock policy is say that okay, this is the list of the pages that you can use. Did it belong to one process only? Okay, let's say you are allowed, okay, to load page in. I think about maybe more than 8, 9, 10, 11, many dot dot dot. Okay, and the OS will have one hand clock, okay, to point, okay, to the frame, okay, that you going to need to be replaced in the near future. Okay, and OS will have one bit to mark on each page. Mark on each frame. Okay, whether that page that load in is just been used or not. They try to do like literally use. The one that never used long time ago, the use bit should be 0. The one that you just used, they change use bit to 1. Okay, they have use bit to identify whether which one you just used. If the use bit is 1, it means that page just been used. In terms of read lazily used, should not replace that one. The one that use bit 0, it means that that frame or that page never used for long time. That one should be replaced. Understand? Okay, they're gonna choose the page to be replaced. Okay, the page that have use bit 0. The one that use bit 1 will not be replaced. Okay. Number 2. Okay, number 1 is a use bit. Number 2, they have hand clock. What is hand clock? Hand clock gonna help searching which page have use bit 0. The page that have use bit 0, that page will be replaced. Okay, and they just go like hand clock, go in circle. What go in circle mean? Just like first in, first out. They go in the order. Okay, but it is a mixing between first in, first out and read lazily used, because they have the use bit to determine which one just been used. But first in, first out, due to the hand clock that go one at a time in circle. That first in, first out. Okay, it's a mixing between the two. Okay, the hand clock do 2 things. Number 1, search for the page that have use bit 0. Then we can replace. Okay, the second job of hand clock is when the hand clock see the page have use bit 1, that page will not be replaced, but that page will change the use bit to become 0. And then hand clock will move. Okay, hand clock do 2 jobs. 1, to search for the page that have use bit 0 so that it can be replaced. Number 2, at the same time, when they're searching for page that have use bit 0, they also change the page that use bit 1 change to 0. See 1 change to 0. If this 1 change to 0, but not replaced. But if they see 0, that one gonna be replaced with a new page. And then change that since you just use it, okay, that just load it in and use it, that one gonna have use bit 1. And then hand clock move. Okay, hand clock move only the time that we need to replace. Okay, hand clock again do 2 things. Search for the page that have use bit 0. At the same time, change the page that used to have use bit 1 to 0. Understand? For example, at this time, if the hand clock is on the frame number 2, okay, and let's say at this time there is a new page need to be loaded into the system. Hand clock gonna start searching for the page that have use bit 0. Okay, so at this time they point to this page, use bit is 1. They say this is 1, it will not be replaced. But hand clock will change the use bit from 1 to 0 and then move. And they see another one have use bit 1 again. Hand clock said it will not replace this one. But gonna change use bit from 1 to 0 and then move. Okay, and until hand clock see a page that have use bit 0, then hand clock said this gonna be the one going to be replaced. So this page 556 will be replaced by a new page 727. And after you replace this one with this new page, that use bit gonna be 1. And after that hand clock move and stop, move and stop. Okay, because it already finds which page going to be replaced. This is a frame number 4 going to be replaced by 727. Understand? Okay, if at this time there is no need for replacement, if the program need to execute this page, that page, those page, no replacement, hand clock remain here. Okay, until there is a new page coming in and need to be loaded in the system, need to replace one of these. Now hand clock gonna start working again. Again, if the new page coming in, what would happen now? Let's see, page number 999 want to be loaded in. 999 is not in here. So now look at the hand clock. Hand clock point to page that have use bit 0. So what does it mean? This one gonna be replaced with a new page. And use bit can become 1 and hand clock move here. Understand? Again, if hand clock is here, if a new page coming in is not in the system, need to replace. Now hand clock gonna search again. Hand clock see 1, not gonna replace. but change 1 to 0. C1 again, change 1 to 0. And now C0, this one going to be replaced. Okay. Hand clock alone is first in, first out. Question is, what is least lazily used? Because you're going to change from 1 to 0. And then soon you come back here, it's going to be 0. It's going to be least lazily used. Let's say, for example, at this time, okay, let's see, we used to have point here, hand clock point here. And we want to replace this one, change 1 to 0. Found this one, change 1 to 0. Found this one, replace. Okay. Let's see at this time. Let's see we replace something. Let's see at this time. Okay, we need page number 45. What would happen? Why is 45? 45 is there. If we need page 45, and then if at that time use bit is 0, use bit gonna change to 1. So by the time hand clock move back to this one, if there's a use bit 1, it will not replace. Understand? Okay, and then flip they found it 1 0, then they replace this one instead of that one. So in other words, why hand clock is moving? If that page is used, that page gonna change use bit to 1. And it means by the time hand clock get to that page will not be replaced. In other words, the page will remain in the memory for one turn. If it in one turn of hand clock, if that page never been replaced, that one going to never been used, that page gonna be replaced. But with one turn of hand clock, if that page is used during that time, use bit gonna change to 1. And by the time hand clock get to it, it will not be replaced. Understand? So a page can remain, actually not 1 round, 2 rounds. Why 2 rounds? Because the first time you load in is 1, right? And then hand clock move 1 round, they'll change this 1 to 0. And then after that, they go another round. During second round, if that page not going to be used, this is going to be replaced. Understand? Okay, the first round of the hand clock moving, that one not going to be replaced for sure. But it's going to change from 1 to 0. And the second round, if it is used, the use bit going to change to 1, and then it's going to remain. Okay, and when it get here, change to 0 again. And during that time, we would use again, change from 0 to 1. Get here, not going to be replaced. Okay, so after hand clock move point, part that page, change from 1 to 0, they have 1 more round going to be used or not. Within 1 round, if it's used, it will not be replaced. Understand? And that's the least easily used. Okay, the let page stay for 1 round of hand clock. If it's used during that time, it will not be replaced. So in other words, it's just been used within 1 round. Just been used, not going to be replaced. Understand? Okay, understand or not? Now look at this example. Okay, here, it is the hand clock. Okay. Star means use bit 1. Okay. Without star, like this example, it means use bit 0. Okay. Okay. At the beginning, we have nothing among these 3 frames. Okay. We just load page 2 in, use bit 1. And then hand clock move. Okay. And now we need page 3. Hand clock is here. This frame is empty. You can load 3 in. And mark use bit 1. Okay, star mean 1. And the hand clock move. Okay, we need page 2, but page 2 already in there. And use bit is already 1. Nothing to change. Okay. Now we need page 1. Now hand clock point here. This frame is available. Load 1 in. And use bit is 1. Again, after load 1 in, now hand clock is supposed to move. But again, hand clock move in circle. Okay. So after the point here, after we place page 1 in here, hand clock gonna move in circle, go there. Okay. Now we need page 5. Okay, hand clock point here. What the use bit of this one? And this time it's 1. They're gonna change 1 to 0. and then move, not gonna replace. And see this one, use bit is 1, change 1 to 0, not replace, move. See this page, use bit 1, not gonna be replaced, change to 0, and go around in circle, Fruit, go back. Now they're gonna go back to C2 that already changed to 0. Agree? Okay, so now the C2 is 0, have use bit 0, they're gonna replace with the new page 5. Okay, so after repeat this, pointer move, the Hancock move. Understand? Again, this one, actually they already go complete one circle. Change 1 to 0, 1 to 0, 1 to 0, come back, now see 0. Okay, in other words, if all of them had used bit 1, it means that from least easily used will become like first in, first out. But that is happened. Okay. Okay, now they need the 2, Hancock is here. Since this one use bit is 0. So since it use bit 0, so then 2 gonna replace this one. And Hancock move. Okay, and now they need page 4. Page 4 is not in here. Need one point to the page that had use bit 0. So then gonna replace this one because use bit 0. Put 4 in. And then Hancock move. And they move in circle. Okay, now they need page 5. However, 5 is in there already. No page 4, no need to move Hancock. Need page 3. Now again, this one, see, use bit 1, change to 0. Move down, don't repeat. C1, change to 0. Move down. Change C1, move to 0. And then move in circle. Now go back to C5, 0. So they can repeat with 3. And then move down. Okay? And now what happened? We need 2. What happened here? Whatever page that we use, we're going to change use bit from 0 to 1. But again, we not replace anything. Okay, but we just use it, change use bit from 0 to 1. Okay? Hancock doesn't move because no need to replace. Hancock move only when we need to replace. In other words, when we have page 4. Okay, at this time there is no page 4. 2 already in here. Okay, no page 4. Hancock doesn't move. But if that page have use bit 0, gonna change use bit from 0 to 1. Okay, and then again now we need 5. Now since Hancock is here, it is one use bit only 1. So if this one use bit 1 should be replaced? No. But use bit 1 gonna change to 0 and then move. Okay, and now they found page that use bit 0. So then they're gonna replace with 5. Okay, and then Hancock move. And now again, this one at this time, this one need page 2. Again, 2 used to have use bit 0, gonna change to 1. Understand? Okay, so this one they have the in terms of implementation. Okay, we use the Hancock, go like first in, first out. Okay, to make it simple algorithm because they use like first in, first out. The Hancock just go neck in circle. Okay, algorithm wise is simple. You don't have to swap anything much. Like literally use every time you pick one page, you have to move your array. Okay, but this one you don't have to move your array. Even though you don't move array, even though you use the time, you still need to check all of them with the time. Okay, but this one doesn't check all of them. They check only the one that Hancock point to. Okay, you don't have to compare all of them. Okay. Okay, but this one you waste one more bit to store the use bit. Okay, on the frame. Okay. This is the performance in terms of these 4 algorithms. Okay, again the way they test the page 4. Okay, optimal is likely to have minimum page 4. Okay, likely because you know the future. Okay, first in, first out is the worst. Okay, least easily used likely to be better than Coq, but again least easily used you have to check many items. Okay, of the whole list. Okay, that the performance of the algorithm itself take longer to run than the clock. Okay, so in terms of page fault, the clock is worse than leadlessly used. But in terms of algorithm-wise, okay, clock you can implement easier than leadlessly used. I mean the complexity of the clock program. Okay, but first in, first out is simplest in terms of development, but it's the worst in terms of page faults. Okay. There are more, okay, in terms of clock. Okay, some of them, okay, they change clock into with more complex. Okay, like they have, okay, the way that hand clock move, okay, and the page that you mark. Okay, you can mark with more than 1 bit. For example, this one mark 2 bit. One is called whether it is legally been accessed and it is legally been modified. Access means to read, modify means to write. Okay. So you could have many criteria to check. Okay, not only the just use or not use, but you have been accessed or not accessed, and also change or not change. Why we need to consider the modify? You know why? Modify. If you copy a page, let's say you have the virtual memory. Okay, likely that virtual memory is big. Okay, if you have the data on virtual memory or instruction on virtual, or let's say data, instruction not likely to be replaced, data likely to be replaced by the program. Okay, so if you have virtual mem and you have the main memory, okay, let's say like the first example, let's say your program needs 10 megabyte, 8 megabyte is in main memory, okay, and then on the virtual mem you can store only 2 megabyte, or you can store the whole 10 megabyte. So you have 8 and 10. 10 is the whole thing. So in other words, you cap the amount of memory in the RAM, but you have a lot on virtual mem. You can store the whole thing in virtual mem and copy the one that you're going to execute in here. But that one also remain in the virtual mem. Understand? If your program is 10 megabyte, you have 8 in the main and 10 in the virtual mem. Copy only 8 of them in here. Leave 2 of them not in the main. Okay, so in other words, okay, if you want to swap out, okay, you swap, let's say you're going to replace page number 3. If you replace page number 3, you're going to copy page number 3 on the page number 3 of the outside. Because outside you have everything. Okay, outside you not really replace. Inside you replace. Outside you put in the same place of that page. Okay, for that case, if the page load in and never been modified, okay, let's say this page number 121, you load it in the main memory, and this page never been modified. In other words, you never change value of this page. By the time you're going to replace, you just replace because the value is the same thing with the outside. Understand? Let's say that page 121, you store 121 in 2 places, in the main memory and also in the virtual mem. Okay, the virtual mem have the whole program, the whole instruction and data, everything. In the main memory you have some of them. Okay, so in other words, in the virtual mem you waste a lot of space, but you don't care because you have a lot of hard disk. Okay. By the time that you need to copy data into the main memory, if that page, which is already stored in both main memory and virtual mem, if that page never been modified, you don't need to write it out. You just replace. But if that page had been modified, before you replace it, you're supposed to write it one outside, because outside is not in the old value. Okay, the inside the memory you have a new value. Okay, so if you manage virtual mem like this, outside you have the whole thing, inside you have some part of it. By the time you replace, you just need to consider whether that page that you're going to replace had been modified or not. If it had been modified, you're supposed to write it out. If not been modified, it means it's the same with the outside. You don't need to write out. You just replace only. Understand? Okay, this is a case that if on the virtual mem you have the whole process. Okay, not like 8 and 2. You need 10 pages or 10, let's say 10 megabytes. Okay, inside allow only 8. Outside you can have unlimited amount. Okay, for that case, if this one already store 8, you can store 2 outside. Or you can have 8 and the whole 10 outside. Understand? Okay, so that's why if you can store the whole thing outside on the virtual mem, then for that case, if you have another bit to identify whether it had been modified or not modified, then sometimes you replace, you don't need to write outside. Huh? Dirty bit? Kind of, okay. Yeah, because dirty bit is a bit that had been changed. Yeah, the dirty bit is a bit that had been changed, and then you have to put it outside. That is a disturbed later on. Okay. They put all 4 of them in here. Same thing. Okay, again, it just try to show you the page faults. Okay, that the optimal is likely to perform with the least number of page faults. Okay, still have time. Okay. Again, in terms of memory management, it's likely that the system likely to have something they call page buffering to store something temporarily. Okay, so the system will have a free list of page with page that is available with page in the list that is being modified, which are not being modified. Okay. And the replacement policy could dealing with also the cache size, which is something that to do with the cache. Okay, if your cache size is small, let's say for example, the cache size is small. It's also similar to this algorithm. Okay, you have to keep copy in and out a lot because cache size is small. If the cache size is big, you're likely not to copy that much. Okay, so in other words, in terms of cache, or even though in terms of main memory, if you have a big amount of frames or have the big large cache, then the replacement policy is least not the most concern because you have big space. Okay. In terms of to let the page remain in the memory, you have fixed allocation or variable allocation. What does it mean? The example that you saw, it is fixed allocation. You keep this process, for this example, 3 frames only, and you never change. It's called fixed allocation. But sometimes think about, if your program run for a while and look like they need more and more and more memory, should we keep replace in and out, in and out, in and out? Let's say compare with another program. Let's say you keep that program 3 frames, that process. But that phase, use only 2 frames all the time. Never have another frame. Nothing to remain in virtual mem. They use only these 2 frames. For that example, some process may have frame left, not really going to use. Even though OS said you have maximum for 3 frames, you can use it, but you're not using it. You have some frame that doesn't use by this process. Why another process like this one keep replacing among the 3 frames? Because the OS capped the maximum to 3 frames. For that case, OS will see that this is not really good idea for the OS to perform replacement all the time, even though some process doesn't use a lot of frames. So it's better, if we could have very high allocation. If the process run for a while, and then OS see that, this page had been using replacement so many times, why don't we grow a little bit more in terms of given frames? Like for previous example, instead of giving 3, look like the one replacement again, we give 4. So then you have less chance to have page fault. If you have less chance to have page fault, then it's Okay, the system or the program can perform or finish the job sooner. Okay. So if the OS could allow variable allocation, in other words, the number of frames could be grow or could be shrink, okay, that would be easier for OS, okay, to let a process to remain in the main memory without doing much of the replacement and page fault. Okay. So fixed allocation, you may have higher page fault than variable allocation. Okay. But what is the disadvantage of this one? Then OS have to keep figuring out how gonna grow this process, how many frames. Okay. Something that you fix, it's easy to implement. Okay, if you keep only 3, never change, never have overhead to dealing with the size of the number of frames. Okay, so implementation wise, this one easier to implement than this one. But in terms of performance wise, okay, this one likely to perform in terms of application could perform faster because the application can reserve more memory. Okay, but this one you fix the number of frames. Okay, so with that one, okay, with the vary size, okay, you may have to also combine with the replacement scope. What is replacement scope? And this is also a big issue in terms of security. Okay, if the process can grow to get more frames, so it means that, let's say you used to have 3 frames to keep replacing in and out. If this process can go to the 4th frame, okay, but 4th frame may belong to somebody else, so then you have to cut down. Okay, another process that used to have 3 and 3, then you have to say this one cut to 2, and that one go to 4. So then for that case, you may have issue of replacement that you can replace outside of the one that you have and shrink another one. Okay, so it could be like global that you place, okay, on any other page. Okay, but if you use them local only, you can grow only whatever you given. Okay. So when you have fixed allocation, you don't need to have global because you never go to outside. Okay, but when you start to have vary allocation, then you may need to go to the another program, another process. Okay. Okay, so you can grow the size. Okay. Again, the OS try to get rid of the page fault. Okay, if you have less number of page fault, okay, in other words, frequency of page fault getting less and less, it means that the system can perform, okay, better, and also program can finish sooner because they don't have to wait. Okay, we try to cut down the page fault. Okay, cleaning policy. What is cleaning policy? Which is the opposite of fetch. What is the fetch? Fetch is you try to load the page in. Okay, either page in when you need demand paging, or you load in ahead of time. Okay, cleaning is the opposite. Okay, when you have to write data out from the main memory to the outside, to the virtual mem. Okay, which is similar algorithm. Okay, you can write the data out to the virtual mem ahead of time. By the time that you need to replace, you can replace immediately because you already write the data from main memory to the outside ahead of time. Okay, so by the time that you need to replace, you just replace. But with the demand cleaning, okay, if the data had been modified and you need to replace this one, you have to wait to write this data out first before you can replace it. Okay, so in other words, you clean only when there is need to clean. But this one, You clean, in other words, you write data out ahead of time. Okay, so which one is better? By the time that you need to replace, the data already been right outside. By the time you need to replace, you can replace immediately. Okay, but this one, if you want to replace, you have to wait to copy the data to the virtual memory first before replace the data on the main memory. So this one you have to wait. Okay, if you want to replace, this one you can replace immediately because data has been right outside all the time. Okay, but this one have overhead because sometimes you not really know that you're going to replace or not, but you just have to copy it. Okay, so system have to keep copy data between virtual mem and main memory all the time, from main memory out to the virtual mem. Okay, so this one likely to wasting the system time to pre-cleaning to the outside. Okay, but you not really know that you're going to need or not. Okay. Actually, in some other system, okay, but it's not the OS. Okay, this idea had been used a lot. Okay, the idea that you have to write the data from your local use to somewhere outside and likely to write all the time. Like for example, you think about